Hi, this is your video for section 12.2 about tests for independence. The objective in this section is to perform a test of independence. So what do we mean by that? Well, in this section we consider contingency tables or two-way frequency tables that we talked about back in chapter 4 at the beginning of the semester. These include frequency counts for categorical data arranged in a table with at least 2 rows and at least 2 columns. We present a method for testing the claim that the row and column variables are independent of each other. A test of independence actually tests the null hypothesis that in a contingency table, the row and column variables are independent. In other words, that they're not associated with each other. The notation for this type of test looks like this. Capital O represents the observed frequency in a cell of the contingency table. E represents the expected frequency in a cell, found by assuming that the row and column variables are independent. R represents the number of rows in a contingency table, not including the labels or the totals. And C represents the number of columns in a contingency table, not including labels or totals. The requirements to do this type of test are that the data have been randomly selected. The sample data are represented as frequency counts in a two-way table or a contingency table. And for every cell in the contingency table, the expected frequency E is at least 5. Now, there's no requirement that the observed frequency must be at least 5. And the other thing about this type of test is that there's no requirement that the population must have a normal distribution or in fact any other specific distribution. To find the test statistic for this hypothesis test, we have a formula, and this symbol here tells us to do the sum, and what this means is that for every cell in the contingency table, we take the observed frequency, which comes from our sample data, minus the expected frequency, we square that, and then we divide that by the expected frequency. To do that for every cell in a contingency table is pretty tedious if we're doing it by hand. A part of the reason for that is that to find the expected frequency in the first place, we have to use another formula, and that is, for that cell of the table, we take the row total for that row that the cell is in, times the column total for the column that that cell is in, and divide it by the grand total for the whole table. Alright, when we're doing the hypothesis test, step 1 is writing the hypotheses. So as usual, we're going to write down the claim or the statement being made. For a test of independence, we're going to write the claim to be that the two variables, that is the row variable and the column variable, are not independent. Another way to say this is that the two variables are dependent or that they're related. Now we're going to write the null and alternative hypotheses, and for these we don't even need to use symbols. We just say for the null hypothesis, it's always going to be that the row and column variables are independent, and the alternative hypothesis will always be that the row and column variables are not independent, or in other words, that they are dependent. Here's an example. Does a pollster's gender have an effect on poll responses by men? A U.S. News and World Report article about polls stated, on sensitive issues, people tend to give acceptable rather than honest responses. Their answers may depend on the gender or race of the interviewer. To support that claim, men were asked if they agreed with this statement. Abortion is a private matter that should be left to the woman to decide without government intervention. We're going to test the claim that the responses and the gender of the interview are dependent. In other words, that it does make a difference what the gender of the interviewer is in how the men responded. So our claim is that for males, responses to the survey questions and the gender of the interviewer are not independent, or we could also say that they are dependent. So our null hypothesis is going to be the responses and the gender of the interviewer are independent. Our alternative hypothesis is that the responses and the gender of the interviewer are not independent, or in other words, that they are dependent. Now we're going to look at the other 3 steps of our hypothesis tests. So calculating the test statistic. In order to calculate this by hand, you have to first find the expected value for each cell of the contingency table. And especially if the contingency table has a lot of rows and columns, this gets very tedious to do by hand. So we're going to look at using StatCrunch to do this. Step 4, the p-value. That's not so hard if you know what the test statistic is. The things that we need to know in order to calculate the p-value are that a test of independence is always a right-tailed test. We're using the chi-square distribution. And the degrees of freedom for this depends on the number of rows, R, and the number of columns, C, in the contingency table. So our degrees of freedom for this is the number of rows minus 1 times the number of columns minus 1. If you have the test statistic and you want to find the p-value with your calculator, you would use the chi-squared CDF function. Since this is going to be a right-tailed test, you would put in the test statistic and then a big number like 10,000 and then your degrees of freedom that you found from this formula up here. Now for the final conclusion, remember that our null hypothesis is that the row and column variables are independent. So if the initial conclusion is to reject the null hypothesis, then the final conclusion is that there is sufficient evidence to conclude that the row and column variables are not independent. We can also say that they are dependent. If the initial conclusion is to not reject the null hypothesis, then there is not sufficient evidence to conclude that the row and column variables are dependent. So this would say that the row and column variables are related or associated in some way. Now let's go back to our example about the responses to the survey question and the gender of the interviewer. Here's sample data that's already summarized in a contingency table. So we have the gender of the interviewer, either man or woman, and the men, this is about the men who were surveyed, the ones who responded that they agree with the question, and those who disagreed. The numbers in this table, this comes from our sample, so this is sample data, so these are the observed frequencies. And we already completed step 1, the hypotheses. For step 2, a type 1 error would be supporting the claim that the row and column variables are dependent when they really are not. And for step 3, we will use StatCrunch to find the test statistic. Here's how we do that. Since we already have the data summarized in a contingency table, then we would basically type the contingency table into StatCrunch. And in order to do this in StatCrunch, you do have to include a column that has the labels for the rows. So we have to put the different values for our row variable in a column by themselves. So I just put this in here as a agree and disagree, and I labeled this column as responses. Then we have the rest of our table. So we have the numbers for the gender of the interviewer being a man and for being a woman. Once we have that typed in, then we're going to select Stat, Tables, Contingency, and in this one, since we have summary data already in the contingency table, we put in with summary. Now what we want to do, where it says select columns, is that we want to select all the columns that have our sample data in them. And again, if there were a total column in this table, we would not want to select that one. But here we selected both man and woman. For our row labels, it does make you select a column for the row labels. So I selected responses. And the column label is optional. I put in gender of interviewer here. And that's just one that you type in. And here's another thing that's optional down here. You can ask it when it gives you the results to include some different values if you want. So I asked it here to include the expected count for each cell of the table. That's the expected frequency that we could calculate with that big formula if we wanted to. And also I asked it to calculate the contributions to chi-square, to our test statistic. So here's what our results would look like. Here it tells us what the row variable is and what the column variable is. It tells us what it's giving us in the table, so it's going to give us the count for each cell, the expected count, and the contributions to the chi-square test statistic. So for example, in this first cell, our sample data was that there were 560 men who said they agree who were interviewed by a man. The expected value for this cell would be 578.67, and the contribution from this cell to our test statistic is only 0.6. That's because the observed frequency and the expected frequency were fairly close relative to how big the expected frequency was. For this cell, we're still fairly close, so we have 308 here and 289.33. The contribution to the test statistic is only 1.2. Same for this one, our contribution to the test statistic is fairly small. Notice for this one, the contribution to the test statistic is bigger, it's 3.15. Now it doesn't look like this number is that much further off than any of the other ones, but if you consider how far it is relative to the expected value here, it's a bigger percentage of the expected value. So that's why the contribution is a little bit bigger here. Now to get the test statistic, which is down here, what actually happens is that these four values get added together. So we take the 0.6, the 1.2, the 1.57, and the 3.15 and add all of those together, and that would give us our test statistic of 6.529. Notice that the other thing it does for you here is it gives you row and column totals for your table. It also gives you a grand total. And it calculates the p-value and includes that down there. So for step 4, we can get the p-value from the StatCrunch display since it does it automatically anyway. If we wanted to calculate it by hand, we'd have to find the degrees of freedom to use our chi-square distribution. So the degrees of freedom for this would be the number of rows minus 1 times the number of columns minus 1. Since there were 2 rows and 2 columns, we'd end up with 1 times 1, which is 1. So our degrees of freedom, if we look back here, our degrees of freedom was just 1. If we want to check the p-value that StatCrunch gave us, on our calculator we'd use chi-squared CDF. We put in the test statistic first and then a big positive number since this is a right-tailed test, and then we put in our degrees of freedom, and on the calculator this gives us 0.0106, which matches with what StatCrunch gave us. For our initial conclusion, if we were using a 0.05 significance level in this test, then the inequality p-value less than or equal to alpha is true because 0.0106 is less than 0.05. This would give us positive conclusions. So our initial conclusion would be that we would reject the null hypothesis. For step 5, our final conclusion would be that there is sufficient evidence to support the claim that the responses and the gender of the interviewer are dependent. In other words, there is an association between the two variables. One thing to be very careful of with this is that the fact that there's an association between the two variables does not mean that one causes the other.